M theory, or in layman's terms, string theory, which is the theory that everything in the entire universe is made up of tiny little vibrating strings that are inside what can only be thought of as a very complicated system. And that's a 10-dimensional Calabi-Yau manifold. Most people have no idea what I just said. I'll try to explain it. The simplest way to think of it is those children's toys that expand into a ball and can crunch down into little spikes. A Calabi-Yau manifold, how we draw them, is kind of like the spike, in the sense that that spike is going to end up being that ball when you put a bunch of strings into it. And the vibration of that string, when you throw it into the Calabi-Yau manifold, ends up determining what type of quark or boson of fermion that Calabi-Yau manifold is going to turn into. That's the simplest way of thinking of it. Going more broadly into details, the Calabi-Yau manifold, being the 10-dimensional space, is the basis for all matter, all space on which matter can exist. Now, this gets into anti de Sitter conformal field theory correspondence, or ADS-CFT correspondence, which essentially states space-time is like a hyperbolic space. What that means is that it's, instead of being straight and flat or curving around special objects, it's like a saddle. And that saddle can keep going and piling on top of each other. And that can create a Calabi-Yau manifold. With the hyperbolic space that exists, we can describe many things, like Einstein's general relativity, and we've even been able to have a quantum field theory come from it. What that essentially means is we know how gravity works. But the problem is, do we really? Now, when we get into the really broad depths of it, string theory at its finest and at its best and at its worst is a mathematical theory. When you look at the math, it gets complicated. It's not that bad, but it's still complicated. The same way that the wave equation describes the probability of an electron being in a certain place in respects to time or not in respects to time in any of the orbitals of a atom. It can be an n equals 1, n equals 2, n equals 3, or n equals 8. String theory describes how matter forms and how everything that we know is based off of quarks. The biggest problem with that, though, is that it's mathematical. Not that the math is the problem, not that the math is wrong in any sense of the word, but rather that it's mathematical and it's not physical. We cannot touch it, we cannot see it, even though it is part of us. Now, with it being part of us, it's kind of hard to rip ourselves apart and see into the finest depths of us. That's why we've created what honestly is a positive in the sense, the LHC, or Large Hadron Collider, in Geneva, Switzerland, run by CERN. We're even creating a newer one. Forget the exact name as of now, but it's about 100 kilometers in diameter instead of just 20 like the LHC. And currently we're running some lead-on-lead collisions at the LHC, which can hopefully give us some new insight into quarks and how they function with the fields in respect to the bosons. We'll have to see with that. We just started that. It's going to take some time, most likely. Higgs had to wait 50 years for his to be proven, so who knows. With that, we've been able to prove things such as the Higgs field, the WZ bosons, multiple fermions with the up, down, top, charm, strange, bottom, tau, electron, muon, tau neutrino, muon neutrino, and electron neutrino. With those, we can fairly easily describe how they are in string theory. Now, when it comes to gravity, there's a bit of a problem. In string theory, it's defined as a graviton, a little closed loop string that keeps vibrating in random, not random, but in very specific patterns to create gravity. The problem with it is that with ADS CFT correspondence is that we can't prove it. Much like Richard Feynman most famously said, if it disagrees with experiment, it is wrong. Now, what that means is that if one little thing proves it's just a slight bit different, we can have a good and decent enough theory, but that theory is never going to predict everything perfectly. So it's not the theory that we should be following. That's a major concern, because with string theory, we can't test it. Not because it's impossible, but it's impossible right now because we need a black hole. And we can either get a very big black hole and have it all suck us all in and not have anything work anymore, or we can create a tiny nickel-sized black hole, which you think that'd be fine, right? Yeah, no, that destroyed the entire Earth. Or we can have a tiny little micron black hole of 250 microns of gold shot by, oh, I don't know, if you're into the sitcom Big Bang Theory, you know he says 2,148 lasers shot into 250 microns of gold to create a microscopic black hole. The problem with that black hole would soon die of Hawking radiation and explode in an explosion that is bigger than both Nagasaki and Hiroshima combined. So kind of hard to test string theory without killing us all. There are ways around it with trying to do it with mathematical proofs, but it just comes out with more math, and that's a problem. Now, it would be less of a problem if string theory was our only theory. We also have quantum loop gravity. Not many people, not the majority of physicists are into quantum loop gravity. There is a slightly large percentage, but not as much as string theory. But that just proves that there's other ideas out there that work just as well or even better at times. Personally, I want string theory to be true. I think it is a beautiful mathematical, and it describes every function of the world perfectly. The problem is we don't know if it's true. Now, with quantum loop gravity, I'm more of a string theorist, but it has its times, it has its moments as a field theory. They assume that there are different speeds of light depending on the color of light, which gets a little crazy there. And again, with string theory, it's beautiful, it's mathematical, and even with the graviton problem, it still works. What's the problem there? The dimensions. We physically exist in 4 dimensions: 3 space, x, y, and z, and then a 4th, time. We can't visualize time that well, and we can't really visualize any spatial dimensions greater than 4. But with string theory, we have 11 total dimensions with M theory, which is string theory now, or if you want to be a bit more precise, ADS CFT correspondence, which is the main one we use for gravity now. With string theory, we've evolved many, many times. We started with, I believe we started with 8, then went to 12, 16, 21. At one point, we even had 38 dimensions. We're down to 11 now, which is a good thing, but that's still a problem, because that's 10 spatial, 1 time. Where is that coming from? Because we exist in 4 dimensions, we see in 2, and we think in 3. Where's the extra 6? Or 7 or 8, if you want to do either of the few. most of the time we just assume that they collapse in on each other and they fold neatly into the three spatial dimensions we know now. However, the problem with them folding is that how do we see if that's actually what's happening? I have come up with a personal theory of quantum fluid dynamics, which more or less describes how the universe would work if it was a beaker filled with the most liquid in the universe, essentially. And that liquid inside is gravity. The simplest way to think of it is as a beaker with a couple hundred milliliters in it. You take a plastic ball, you dump it in, and the water moves around it. That's how liquids work. They take on the shape of the container. The universe expanding even is that container, and the fluid inside is gravity, made up of molecules that I am dubbing gravitons simply for the sake of simplicity, nothing more. With those gravitons acting as the H2O molecules would in water, we can expect to see a hydrogen atom as our plastic ball moving through that quantum fluid of gravity. We can expect to see the hydrogen atom that is moving through a quantum space that is supposed to be empty. We can expect to see gravity acting as a sort of, exactly almost as a fluid actually, where it is moving and bending and shaping around it. Now, as this hydrogen atom is interacting with these particles, almost, they are gaining charge, which again is sake of simplicity. It's more just saying that they are becoming active. They're like the excited electrons of a carbon atom, where they're jumping from valence electron to valence electron, moving all around. When that's moving through, those particles are going to create the field of gravity around that object. And all the others in the universe will still be those same particles, but they don't have that action acting on that particle at the same time. And they can create these gravitational waves, not the same type as black holes do when they're circling around each other, creating mass distortions in space and time, but more so in the sense that the gravitational waves are what's connecting two objects together. Say I take a bowl. A simple way to think about it is the same way you would think about the simple explanation for general relativity. You have a trampoline, take a bowling ball, put it in the middle, the trampoline bends. That is general relativity, kind of. Now take a second bowling ball, move the first one out and put it at the side, put each on opposing sides. That space-time is going to bend towards the middle, and they're going to start rolling around and meeting in the middle eventually. That is kind of how it would work with gravitational waves at the quantum scales with quantum fluid dynamics. QFD, if you will. I'll shorten it from here on out. With QFD, and those acting as the way they do, those waves are the curvature in space-time that we are seeing with Einstein's general relativity. Now, this is not meant to discard any part of what makes string theory able to confirm the existence of fermions and bosons. This is meant to be a quantum theory of gravity that is meant to introduce us to a new way of thinking and allow us to create models for how the universe expands, because even with string theory, without dark matter and dark energy, it's hard to express the expansion and acceleration of the universe that we are seeing. With this, we can see it in a sense But the more important thing we can see is we can see why Einstein's gravitational wells that form around a object, say I have a planet-sized object right next to me. A gravitational well is not going to be, take a well in a bucket and dump it down all the way. This is going to be that curvature in space-time. That's going to be the trampoline bending under the bowling ball. We expected to see those growing every little bit, but they're not at the place we thought they would be. They're a little behind. QFD allows for the explanation of why that's happening, because what that does is shows that as the universe is expanding and accelerating, the liquid inside of it, which is gravity, is moving out with it. So although the planets are still being, all the orbital bodies, celestial bodies, stars, planets, etc., are still being affected by gravity, what happens with that gravity is that it's kind of getting stretched thin. It's like a rubber band, or just a plain piece of rubber that you keep stretching, and it keeps getting tighter, tighter, until you can't bend it down anymore in the middle. When that happens, it starts to bounce up a little bit. That's what we're seeing here. We are seeing the effect of gravity filling up a space and how that is shortening the wells that we are seeing. Not in the sense that they're becoming weaker, but because they are not at the place we expected them to be. And we can expect to see that they're not going to be there for the next while, and eventually further on in the universe, if we were to have one of three possible ends to the universe. We have the big rip, the big crunch, and the big bounce. Big rip, big crunch, and just the heat death. What this is showing is that there's probably going to be a big rip with the acceleration of the universe, beating out gravity, because as gravity is expanding and moving with the universe, it's becoming weaker. And as gravity becomes weaker, dark energy is just staying the same, and that's going to start ripping apart stuff. The same way a black hole would rip you apart if you were to stand next to it. You would undergo spaghettification, eventually being halved an infinite amount of times.